let's talk about the second strategy. So instead of using a sim set, this time we try to use a sim map that will also keep track of the parent node that we got a node from. So we will call this map parent, and then we iterate through the neighbor of a node. We ignore the parent node, otherwise it will be detected as a trivial cycle, right? So, and we know that the parent node has already been visited by the point anyway, right? So the starting node is 0 in this implementation, and it has no parent. So we put it as -1 as our default value. So at first, it is a little more difficult to understand why this strategy even works. A good way to think about it is we should remember that, like the first approach, so we just want to avoid going along the edges that we already been on. That's the edges in the opposite direction, right? So the parent links will prevent that, as each node is only entered for exploration once. So imagine you are walking through a maze with the condition that you are not allowed to go back along any path you are already been on. If you still somehow end up somewhere you were previously, then you must be in the cycle. So first, let's print out the adjacency list we just get, which is the 5 nodes 0 connect to 1, 0 connect to 2, 0 connect to 3, and 1 connect to 4. Then we initialize a map parent. We have node and parent. So first, we make the -1 is the parent of the node 0, and we record it. So first, we set a stack list and initialize an element 0 into it, and then we pop this 0 into the node. Now the node is 0, and we check the adjacency list at 0, which is the children's nodes of node 0, which is 1, 2, 3, and then we use a for loop for neighbor in the adjacency list at 0. So first, let's check when neighbor is 1, and we compare the neighbor with parent at node. Of course, 1 is not equal to -1, so we can put 1 into the map parent. We just record 0 is the parent of the node 1, and then we append the 1 to the stack, because stack was empty before it is pop out. So secondly, when 2 is the neighbor, we compare 2 with -1, which is the parent as a node. 2 is not equal to -1, so we put 2 to the parent set, which is 0 is the parent of 2 node, and then we append 2 to the stack. And thirdly, when the neighbor is 3, we compare 3 with -1. 3 is not equal to -1, so we put 3 to the parent map, which is record 0 is the parent of node 3, and then we just append 3 to the stack list. So now, because we are run out of the neighbor in the adjacency list at node 0, so we should go back to pop the stack. First, we pop the 3 from the stack into the variable node. So now the node is 3, and we check the adjacency list at 3 is have only one element, which is the neighbor is 0. And we compare the neighbor 0 with the parent as node, which is also 0, so they are equal. So we have to continue to skip this trivial cycle. So secondly, let's pop 2 from the stack into the node variable. So now the node is 2, and the adjacency list at 2 is 0, neighbor is 0, and we compare the neighbor with parent as node, which is also 0. So we should skip this trivial cycle. So thirdly, let's pop the 1 from the stack into the node variable. Now the node is 1, so adjacency list at 1 have 2 children's nodes, which is 0 and 4. So now let's start when neighbor is 0, and we compare it with parent as node, which is also 0. So we skip this trivial cycle. And then we check when the neighbor is 4, and we compare it with parent as node. 4 is not equal to 0, so we put 4 to the parent map, and then we just record 1 is the parent of the node 4, and then we append this 4 to the empty list stack. So now we are run out of the neighbor in the adjacency list at node 1, and now we should go back to pop the stack. So we have only one element in the stack, which is 4. We pop the 4 into the node variable, which is node is 4. And then we check the adjacency list at 4, which we have only one element, which is neighbor is 1. And we compare this 1 with the parent as node, which is also 1. And we should skip it because it is a trivial cycle. So finally, because the stack is empty, we should break up the while loop while stack, and then we should check the length of the parent, which is 5, which is equal the n, which is also 5. So that means we already traverse all the nodes without missing it, and then we should return true because there's no cycle or trivial cycle. It is a valid tree. So here we use a map to keep track of how we got into each node. Let's initialize the variable parent. And it is a map, and first it have element 0. The node 0's parent is -1, which means it is a root node. And then we use a stack, which is a list. We initialize the element, first element 0, and then we use a while loop. While there's a stack, there's a nodes remaining on the stack. Every time we pop the last element from the stack into the node, and then we can use our for loop. We will check the unseen neighbor of the node. So we use a for loop for neighbor in adjacency list at node. So it will check the every children's nodes of the adjacency list at node. By this for loop, first we should execute the trivial cycle. If the neighbor is equal to parent at nodes, that means it is a trivial cycle. If it is a trivial cycle, we just skip it by continue to a next, skipping to a next neighbor. Another edge case is if we have already seen this node before, if the neighbor is in the parent, that means we have already seen these nodes before. In that case, we should return false, because if it is we have already seen before and then we have seen again, it will form a cycle. If it is cycle, then it is definitely not a valid tree. So we return false to indicate that it is not a valid tree. So if we skip these two edge case, then after that we should record it have been seen before. So which is the parent at neighbor is node. And after we record this in our parent map, we put our neighbor onto the stack, which is stack append by the neighbor. And after this for loop and while loop, finally we just check return the length of the parent and the nodes n. So if it is equal, that means it is fully connected. All the nodes have been right into the parent. It is fully connected, that means it is a valid tree, so we return true. So the best strategy for this problem is probably the second one, because it doesn't require us to modify the adjacency list. But for more complicated graph problem, sometimes the first strategy can be very useful though.